Welcome to Mr. Frolic's physics classes. In this video, we're going to discuss impulse and momentum.
Hello there. We have, in our study of mechanics, already learned how to describe motion, already learned how a force will impact motion, and even how much energy a moving object carries with it. Today, we want to think about something else regarding motion. We want to try to quantify motion. By quantify motion, I would like to be able to measure the quantity of motion an object has. And the technical name for quantity of motion is going to be called momentum, and we represent by a letter P. Don't ask me why P, I really don't know. Once I start studying physics in my life, it was already called P. In order to define or to see how we can quantify motion, I will, at this point, reason this way here. I have an object moving with a certain velocity v. And I want to stop this object in a certain time. So I want it to come to a stop. For that, I would need the action of a force in the opposite direction to make this object come to a stop. So this moving object had some quantity of motion, some momentum. And this force here, acting on the opposite direction, made it come to a stop, which means it ended the momentum of that object. Well, the more force I need, I would assume that more momentum needs to be removed, more momentum I need to change, and therefore more quantity of motion I had before. One thing we can reason is that the same object, but moving with a velocity v2 greater than my initial velocity, if that was my initial velocity, would require more force to come to a stop, would require a bigger net force to finally come to a final velocity of 0. And then I can say that the momentum of my system is going to somehow increase with the velocity. So I can say that momentum is somehow related to the velocity or speed. Now I don't know if that is linear, quadratic, cubic, so I'm just going to call this here v to the a power. Let's also consider two objects moving with the same initial velocity v1, but the second object is more massive than the first one. Which of the two requires more force to reach a final velocity equal or equals to 0? And we have that the more massive object would require a bigger force to stop than the less massive object to stop on the same time. So what we have is that the more massive object had more motion, more quantity of motion. The more massive object had more momentum than the less massive object. And therefore, we can also say that momentum is going to be proportional to the mass of the object. We don't know whether this is directly linear, quadratic, whatever, so I'm just going to do proportional to the mass, the b power. If I have a proportion this way, I can combine it in one sentence. Momentum equals to a constant proportionality, m to the b power, v to the a power, where k, b, and a are coefficients that I still need to adjust. The thing is, even if it does not look like that, we always try to set science the simplest possible. So I will define those coefficients the simplest way possible and see if my definition for momentum of a system, of a particle, will work this way. If it does, life is good. If it does not, we need to come back and maybe aprimorate this. So the simplest possible value for the constant k is 1, for the coefficient b is 1, and for the coefficient a is 1. And if I apply those to my equation, momentum can be rewritten as P equals m times v. We will also find in our studies that this quantity of motion should have vector properties. And therefore, we'll define this not as mass times speed, but as mass times velocity. And this is our definition for the linear momentum of a particle of mass m moving with velocity v. The international units for linear momentum are going to be unit of mass, kilogram, multiplied by the unit of velocity, meters per second. And this does not have any special name. After defining momentum, we now can actually see how Newton's second law can be defined or can be written in a more grown-up way. So basically, the way we can word Newton's second law is to say that the net force or an unbalanced force on a system is going to be equal to the rate of change of the momentum of an object. Or net force equals to rate of change means time derivative of the momentum of an object. But we have that the momentum is given by the product mv. And now here I need to use the product rule. So net force. So we have that net force is the time derivative of mass times velocity. Or, if I apply now the product rule, this will be the derivative of mass multiplied by velocity plus mass times the derivative of the velocity. If my system has a constant mass, then the derivative of mass with respect to time is going to be 0. And net force is reduced to m dv dt. But dv dt is acceleration. And then we have that net force is mass times acceleration. So as you can see, Newton's second law, the way we've learned and we've been using so far, is actually a particular case of the more general definition, which is changing momentum over time when mass remains constant. After seeing the relationship between Newton's second law and momentum, let's talk about the concept and then define, impulse of a force. But before I define impulse of a force, I would like to talk about the idea of an impulsive force. So, what is an impulsive force? It is a force that has a very large intensity and that acts during a very short time interval. If I graph the force as a function of time, an impulsive force would have a graph that would look very much like this here. It's 0 for most of the time. It spikes suddenly to a very large value and then comes back to 0. This force is a force like this is a typical situation of a collision, two objects crashing against each other, or perhaps of an explosion. Okay? And impulse of a force, although it can be defined for any force acting on an object, is more meaningful when we are discussing impulsive forces, systems with impulsive forces act on it. Well, the impulse of a force is by definition the change in momentum of an object. Okay, so if I'm applying a force on an object, the impulse of that force is going to be the change in momentum of that force. If you remember Newton's second law, which I can rewrite as this way. If now I take the integral on both sides, we're going to get that the change in momentum is going to be the time integral of net force multiplied by time. So, if now I combine this equation here, the definition of impulse, with the equation we just derived as impulse equals the integral of net force multiplied by time, what we'll get is that the net impulse of a force acting on an object is going to be equal to the integral of net force multiplied by time, or sorry, the time integration of net force. In terms of units, impulse is given then as Newton multiplied by second. And I'll leave for you a verification that 1 Newton second is the same thing as 1 kilogram meters per second. Okay? And neither of these units have any special name. One last observation still on this board. Let's remember that the integral of force over time is actually the area of the force for the force versus time graph. So the area of this graph here will give me the impulse of the force. A very useful relationship between kinetic energy and momentum. Okay? Let's remember that kinetic energy is 1/2 of mass times speed squared. Now, if I multiply top and bottom by m, what I get is this here. Kinetic energy equals to 1/2 of m squared v squared divided by m. But mv is momentum, and so this equation can be written as kinetic energy equals momentum squared divided by 2 times the mass. Notice from this equation here that if objects have the same momentum, kinetic energy will be inversely proportional to mass. Therefore, a more massive object will carry less kinetic energy. A less massive object will carry more kinetic energy. As an example, let's say that we kick a ball with some momentum and shoot a small bullet with the same momentum. The kinetic energy carried by the bullet would be significantly bigger than the kinetic energy carried by the ball. If the ratios in mass is 1,000 to 1, the energy is going to be 1 to 1,000. So the bullet will cause significantly more damage as hitting you than a ball. On the other hand, if my kinetic energy is constant, I can rewrite this equation this way. And for a constant kinetic energy, momentum is going to be proportional to the square root of mass, which means that more massive object carries more momentum. Let's now address the relationship between a force on an impact on a collision and the impact time. Okay? So I'm going to assume the idea of an object that is moving with some initial momentum and somehow will come to a stop. This object will undergo some change in momentum, and the impulse of the force equals that change in momentum. The impulse of the force is force multiplied by time equals change in momentum, and then force is going to be change in momentum divided by time. What we have is that the required force is inversely proportional to time. So on a given collision where some amount of momentum will change, we have that the longer the object spends changing, less force is required. A typical scenario of this is, for example, a car that will come in and crash against bushes, or the same car crashing against a brick wall. And when the car crashes against the bushes, the time it takes for the car to stop is big. Therefore, the force acting on the car is going to be small, and the car is going to be small, not that much damaged. But when the same car with the same initial momentum hits a brick wall, the time to make the car stop is going to be relatively small. And that means that now I need a huge force to stop that car. And with this, the car is going to be more damaged. When we use our cell phones, for example, a cell phone, and we drop the cell phone and it hits the ground, almost always that means a cracked screen. What we all do with it, we put some kind of plastic cover around the cell phone. And basically what this does is that it gives a little bit while the phone is crashing against the floor. This will increase the time of the collision, of stopping the phone, a couple times, 5, 10 times. And that decreases the force applied on the phone, hopefully saving the screen. When a person jumps, from a certain height on the floor, naturally speaking, instinctively, we kind of bend our knees when we do that. Well, bending the knees increases the time of that we're taking to stop, and therefore decreases significantly the force, the impact force on our feet, knees, and our back. If you actually jump and try to land without bending your knees like this, you are extremely likely to get injured and get hurt. Last example I would like to talk about is the use of airbags. Well, an airbag is nothing but just a cushioning thing that will pop in front of you in case of an accident. So as your head and your body, upper body, is moving towards the dashboard or the glass, the airbag is going to inflate and will increase the time stopping your body. So instead of stop at once, you're going to stop for a longer time, and therefore you're less likely to get injured. Still talking about the relationship between force required to stop something and time of impact, let me talk about bouncing. Is the idea of, let's compare a clay ball moving with a certain momentum and a rubber ball moving with the same momentum and colliding against the wall. The clay ball will just smash against it, whereas the rubber ball is going to bounce back with some final momentum. Let's assume, just for the sake of this conversation, that this collision here is perfectly elastic and that the final momentum is equal to negative the initial momentum. So it just reverses direction. The change in momentum for the clay ball is just going to be negative the initial momentum of the system. But the change in momentum for the rubber ball is going to be twice as much. And if those collisions happen roughly during the same time interval, that means that the force here on the rubber ball is going to be bigger than the force on the clay ball. Two applications of it. One is this picture that I'm putting right now, and I found this on a book. I don't really remember where it was, perhaps on Hewitt's book, The Conceptual Physics, but I'm not really sure. And it shows an improvement of the idea of the water wheel. So instead of having flat pedals where the water would bounce and splash, okay, you can see that that water wheel had a curved pedal in a way that the water would bounce back. So instead of hitting and splashing, the water bounces back. But when the water bounces back, it actually, the change in momentum of the water is bigger than when it just stops. And this will then produce a greater impulse of the water on the water wheel, making the water wheel spin faster, thus increasing its efficiency. I also remember my karate master, when I did karate, and he was training us to break tiles and some people coconuts and stuff, that he would say that the maximum damage will be caused when your punch bounces back. So he would say you need to punch or kick in a springy way that bounces back. I never mastered this technique, but people who did could produce more damage, could produce more impulse on the other object, and then they were more effective in breaking the tiles, ice bars, or coconuts in our demonstration. This concludes the lecture on impulse and momentum. What we should do now is practice some problems to see how we can make this work. And in the next lecture, we're going to talk about momentum of a system of particles and also about the idea of conservation of momentum and see how Newton's third and first law can fit into this. Example 1. We're given that a 3 kilogram object is under the influence of a 12 Newton force, and its velocity increases from 10 to 18 meters per second. And the mass of this object is 3 kilograms. And we are asked to find what impulse is given to the object and also how long has this force acting on the object. I'm going to ask you to stop the video, calculate this, and then check my solution. So, to find the impulse, let's remember that impulse equals change in momentum. And change in momentum is mass times final velocity minus mass times initial velocity, which is final momentum minus initial momentum. So in terms of magnitude, this impulse is going to be then 3 multiplied by 18 minus 10. So this impulse is 18 minus 10 is 8 times 3, 24 Newton second. In order to find for how long the force applied on the object, I'm going to use the other definition of impulse. So impulse, we saw, is also force multiplied by time. So time is going to be impulse divided by the force. And that then is going to be 24 over 12. The time elapsing here now is 2 seconds. So these are my answers to the first example. Example number 2, we'll talk about an object of a mass of 10 kilograms that moves along a straight line with a constant velocity of 10 meters per second. So this object is here, moving this way, 10 meters per second. A constant force acts on this object for 4 seconds. And at the end of these 4 seconds, so this was t0 equals 0, and at the end of those 4 seconds, t prime equals 4 seconds, the object now has a velocity of negative 2 meters per second. They want to know the impulse acting of the object and the magnitude of that force. I'm going to also ask you to tell us the direction of it. Please take a minute to calculate this and then come back to check my solution. Well, let's see. First thing, it's not explicitly given, but it is implicit that we're choosing a reference frame positive to the right. Well, impulse equals change in momentum, which is going to be then my final momentum minus initial momentum. I'm not writing momentum as a vector right now, but I'm going to use the positive and negative to give information about its direction. So I have that impulse is going to be then my final momentum, which is 10 times negative 2, minus my initial momentum, which is 10 times 10. So impulse is going to be negative 20 minus 100, negative 120 Newton second. Notice that this negative here means that this impulse is in the negative direction, which you could have inferred just reasoning that if my object is moving initially in the positive direction and then it turns back into the negative direction, a force into the negative direction should be acting on this object. Now I want to know the magnitude and direction of that force. Well, remember that impulse is force multiplied by time. So force is impulse over time, and then the force is going to be negative 120 divided by 4. And that's going to give me negative 30 newtons, meaning 30 newtons in the negative direction. Example number 3. A 1 kilogram ball strikes a wall with a speed of 2 meters per second and bounces straight backwards with a speed of also 2 meters per second. What is the change in momentum of the ball? Please work your solution and come back to check mine. Well, on example 3, we have the incoming speed of 2 meters per second, the returning speed of 2 meters per second. One thing that we need to do is set a reference frame for the positive and negative, for the directions. And I'm going to call my reference frame positive to the left, this way. Let's remember that I can do this perfectly fine. But on this reference frame, the initial velocity of my particle was negative 2 meters per second, and its final velocity is now 2 meters per second. Well, the change in momentum is going to be final momentum minus initial momentum. And then that is the mass of the object, which is 1, multiplied by the final velocity, which is 2, minus the mass of the object, 1, multiplied by its initial velocity, negative 2. So the change in momentum is going to be 4 kilogram meter per second squared. If by any chance you found 0, that is a perfectly normal conceptual mistake. It's really because you forgot the negative and the positive. And that is explored a lot in exams. This concludes our lesson about impulse and momentum of a particle. The next lesson, we're going to talk about the momentum of a system of particles and the conditions where momentum is conserved or not conserved, and how Newton's laws fit with momentum. See you around.